All right, I think we can get started. So, good evening, everyone. Thanks for joining on a Saturday evening. Yeah, welcome to the LLVM Social Bangalore talk. This is a series of talk on common compiler tools. And if you missed the previous talks, you can find them on YouTube. It's recorded and uploaded as soon as it's done. And yeah, let's get into the talk. I hope you guys can see my screen.
Yeah, we can.
Okay, cool. So this talk will focus on C-reduce. So what's C-reduce? C-reduce it was developed. It's a tool that was developed and maintained by John Reger and his colleagues at University of Utah. It's a test case reducer for C, C++, and OpenCL as it was initially started. It does a credible job of reducing test cases in other languages like C, C++, like Java, Rust, Julia, Haskell, Racket, Python, SMTlib, and other languages. So why is this talk relevant? So just not to bore you for some time, I just want to give you a motivation for this talk. So why test case reduction is important? Test case reduction can generate programs that misbehaves quickly uh, and reducing the number of function calls, memory allocations that the developer has to step through and reason about while debugging. So basically, it's just that you don't want to waste resources and time debugging a large test case. The reduce file contains a little code not directly relating to triggering the bug, reducing the likelihood that the developer will be distracted by extraneous features of the test case. So if you have a large test case and you want to focus on the test that matters or the region of code that matters and not get distracted away by a larger test case, the other portions of the code. Reduced test cases for the same bug often look similar. So if you have a lot of reduced test cases for the same bug, it will often look similar. So you can think of it as a canonical representation of the code that induces the bug, unlike unreduced files that often look a little different. And there is often little or no discernible similarity between unreduced source file and its reduced version, making it easier for bugs triggered by proprietary code to be reported externally. So if you have code base that sort of has your IP, but you still want to contribute that code or file a bug against LLVM project. Let's say you're a user of LLVM and you want to share code that's proprietary, like code in your proprietary test suite, and you want to produce a reduced version of the test case that can be triaged by folks in the community. You can provide a reduced version, and this reduced version does not have to be very similar to the one that triggered the failure or segmentation fault for that matter. And especially if you're working with LLVM and run it a bug, you should be able to debug it quicker, which also depends on the size of the file. When you file a bug for that, again, you have to produce a reduced test case to increase the odds of getting it fixed. So before getting into the actual technicalities of the talk, let's do a demo. Hope this goes well. So this is a C-reduced demo, so we're not going to do hello world. We can just do hello. So okay, here. So what you're seeing is hello and not world. And so let's do some unnecessary details. So there are two parts of the program. One is a reduced test case like hello world.sh that actually runs the code, and hello world CPP. So this is a code. Oops. So this is a code that I have. So here it just outputs hello and world in a new line. So what we want to do is we want to just remove world and just print hello, and you want the program to determine it automatically. And what you do is you have a script like this, and we'll go over what the script does in a larger test case. But for that matter, you compile the test and you output it, and you just grep for hello. So this will tell the the reducer program to just look for hello in the code, and whenever it tries to remove region of code, and compiles and runs it, it makes sure that the the test that the output that it gets is the same as that output that is expected. So, let's say I'm running CWise here. What is sh? That's a program that you give that tells it that tells a program to run. And so typically it takes a minute for this hello world to run, so just bear with me. And while it while it's going through, if you look at the output that's generated, you can see a lot of Clang related passes as that's run. There is a line pass that removes line by line, and we'll go over what happens inside it, but it's just to give you a feel of what happens when you run the test case, or when you run the C-reduce or C-wise program. Well, hopefully we are almost there. Cool. So if you can look at the last line, you can see that it was able to determine that the world is not relevant for the piece of code. We just want to say hello, and we don't want to say hello world. So the second to the cout statement was unnecessary. So it was able to determine that we just need just the first line. So that's the reduced the hello world version of reduce here. And hope you can get a feeling of what the program does. So let's go to the slides. Cool. So we're just going to look at the history of test case reduction. So the history of test case reduction dates back to 1990s with differential testing. So what is differential testing? It is a software technique that attempts to detect bugs by providing same input to a series of different applications. So let's say, for example, two different applications like Clang and GCC, and you are observing the differences between their execution. And you want to say which code is better, and whenever there's a change in the output, you try to you know uh, it, try to correlate the differences and find if there's a bug. But the first actual study started in 2000 with Hilbrand and Zeller with the delta debugging. So delta debugging is the basis of most of the tools that we'll talk about in the coming slides. Delta debugging algorithm is a general purpose technique for the test case reduction, which simplifies some of the failing input to a minimal test case that produces failure. So this is similar to what C-reduce does. It uses a greedy search where a series of variants. So variance is a subset of the program that causes the failure, and is produced by removing each chunk of the test case. When no minimum size chunk can be removed from the test case without breaking the property that triggers a bug, the delta debugger terminates. So you iterate till some sort of a fixed point, and then you terminate it. It's a line-based remover tool, and it could recognize a file in such a way that all nested curly braces are deeper than a configuration level would appear on a single line. So it does on a line by line basis, and it also accounts for some structure. But yeah, we'll come to see what are the advantages of C-reduce over delta debugging in the later slides. Yeah, and so this is when during 2008, John Rager started interested in C-reduce when they were finding a lot of compiler bugs using random testing. So they also have another project called CSmith, which generates random C programs, and using that they reported around 500 compiler bugs. And what he noticed was that they were producing larger code, and they want to file bugs with a reduced version. So they were using Delta debugging tool developed at UC Berkeley, which is based on Delta debugging that Zeller and team developed. It was a line-based reduction tool that it removes line from source program to reduce it. They noticed that the tool got stuck in local minimum and was not able to exploit enough structure of the file being reduced, like simplified arithmetic expressions. So what it does is that they noticed that C-reduce was able to do better smaller programs, or even a hand driven reduction was able to do much better job in case of some programs that delta debugging failed to do. Uh, so this is when John Reger started to develop C-reduce as a full-fledged tool, and they got inspired by Delta's design, the Delta debugging tools design, and they kept two aspects of the design: the configurable hierarchy reformatting of a test case based on a curly brace nesting. Uh, so they have, so every program has this hierarchy. Most C or C++ program has this hierarchy of curly braces, and they want to have they want to understand this hierarchy like a block versus a function scope, and using this you can remove multiple functions at a time, for that matter. Delta's mechanism for determining whether a given variant is interesting by invoking a user supplied program, typically a shell script. So this is powerful. Uh, you know uh, Offloading whether a variant of a program is interesting or not is and offloading that to a script is as a powerful technique, and they kept that for C-reduce. And as you've seen in the demo, that there's a hello world.sh bash file that does this test whether the output from the program contains the hello string. The interestingness test can discard test cases that trigger certain compiler warnings, and it can attempt to disambiguate different crash bugs. So the interestingness test is the script that runs a program and looks for certain compiler bugs. Let's say you have multiple compiler bugs and you want to target just one of it. This script allows you to do that because you can just focus on the specific output from the compiler, and then you can throw away other errors and have a program that's reduced that just um, you know ge- generates that specific warning or a compiler bug. So what does that interestingness test focus on? So this is the thing that you have to design on your own by hand, and what that test need to verify whether variant is well defined by the C or C++ standard, and does the variant avoid depending on behaviors that are unspecified by C or C++ standard. Does the buggy compiler turn the variant into an executable, because you want to run this program in order to for the compiler to to generate some output. Does this executable terminate with a specified time? So this is very important because you cannot have uh, programs that compile forever, that stuck in an infinite loop during compilation. Does the reference compiler turn the variant into an executable, as in that there is no bug? Does the behavior of two executables differ in a way that indicates the miscompilation has occurred? So what you have to do here is that you just have to design a program that that you have to say that this variant is interesting, such that the output or the compiler bug that's triggered, that's interesting for you. So it takes practice to write an interestingness test case. So it took some time for me to write that hello world interestingness test case, because I want to take hello world and hello and not the world. So I initially wrote grep for hello and not for world, but that's not possible because whenever you output hello world, world is also there, and so it takes time for you and practice to write the interesting test case. Yeah, it comes with practice. Yeah. A small code that invokes a collection of pluggable transformation passes until a global fixed point is achieved. So um, C-reduce has a configurable small core that invokes a reducer and has a pluggable transformation. So this is similar to how a compiler would work. It has a smaller a structure where it has you can write transformation passes on it. So this is similar to how a compiler would work, and that collection of transformation passes, and here you have to iterate until here you have to run these transformation passes until you reach a global fixed point. The fixed point being that you cannot reduce you cannot reduce the test case further, and that it still produces the compiler bug or the thing that you're looking for. The transformation passes are stateless, so they don't take into state. Uh, and whenever you run it twice, the first run does not affect the second run. Sequence of transformation passes is carefully orchestrated such that the passes are likely to give the biggest wins. So this is like configuring your pass order for a reduction, such that, for example, the mlir-reduce has a line reduce or a line pass that removes lines at a time, such that you remove entire functions in the first few transformations, such that you don't end up simplifying much simpler expressions. So it's carefully tuned. It also performs test case reduction in parallel using multi-cores. So if you have multiple variants of the same program, so you start with a single program and you do some sort of a tree-based uh, reduction, and you each the branches of the tree, you have a variant that's different from the other, and you want to test them in parallel. So that's much more powerful, because you want, even for the small example, it took more than a minute, and you'll see in the future demo how long it take for a much larger test case to run to reduce. So it's parallel. And so this is from John Regger's blog on what are the test cases that they run. So they have 35 passes that's written in Perl that removes lines, remove various kinds of match delimiters and shrinking integer variables. And they have 6 passes that reach out to other tools like uniftf. So uniftf is a tool that does pre-processing for you, and Alexa for C++, that supports various token level reduction transformations. And they also have 69 passes that are implemented in C++ that uses Clang frontend. So we'll look at how Clang frontend is being used in the next talk, where we talk about Clang tidy and Clang format. We'll look into how Clang is being used as a library for that. And but for that, but for here, for the sake of simplicity, Clang can be used as a front-end library that does source-to-source transformation. So it'll give you an AST, and you can do source transformations on that. And here they do function inlining, partial template instantiation, scalar replacement of aggregates, copy propagation, and eliminating levels of class hierarchy. So these are even compiler optimization techniques, for example, copy propagation, SROA. And you can see that this function is more like a compiler optimizer, but this is uh, there are some differences that you can see, because your reduced test case does not it's not an optimized version. So real world demo. Yeah. So this is a bug that was reported in upstream. So I just looked at LLVM issues and looked for some interesting test case. So this was a front end bug that was reported, and the user attached close to around a pre-processed file that's around 24,000 lines of code, and it seg faulted when you run the compiler with a specific set of options. So this is the test program that I created. So this is the compilation that triggered the seg fault. And you can see I'm using the upstream Clang, and it passes the list of options, and the program is called multi-return.cpp, and this is what triggers a seg fault in the compiler. And what we're going to do is just run the script, and just look for seg fault. I'm not an expert in writing shell programs, so it's hard for me to write a program that captures a segmentation fault. So I wrote a trap that echoes segmentation fault, and then I wrote a second shell script that runs the first shell script and outputs that to an output log and looks for segmentation fault. Yeah, it's a convoluted way. Like I said, it takes practice and time for time to develop those interestingness test cases or the script. So so this took me an hour to run, to reduce this 24,000 lines of code down to close to around 5 lines. and when I run this output, I can still reduce. So this is the test, and when I run that test, it's able to seg fault, and you can see it provides a trace, and hopefully we can see where the bug is. Yeah, cool. So it's able to trigger a compiler bug, and you can see that if you run into a actual LLVM bug, you can see that they'll ask you to file a bug on LLVM issues and crash, include the backtrace, preprocess source, and associated script. And this is what the user did. He attached a preprocessed version, and it's advisable to provide a reduced version if possible. And so I think I'll just show you the way I run, but I can guarantee that it will take a while to run. You just need two files. So you might see that CWise was so this is something that I failed to mention, that whenever you run the test, the interestingness script, it actually looks for the script to uh, provide a 0 or 1 return value. So whenever it returns a 0, it means that the variant is an interesting test case. If it returns a 1, or I mean anything other than 1, it's a non-interesting one. So what here it says that it should result in 0, right? Oh shoot, I think I copied the wrong one. Yeah, I think yeah, live demos are always bad. So CWise, you provide a reduced the interestingness script, and you pass the program. I hope it works. Nope. Yeah, I think this is how you run it, and yeah, I'm not sure what's happening right now, but this is how I did it, and yeah, it just gave me a reduced test case like this. And one more interesting thing, that when I formatted the code, so you can do that through Clang format, the bug is not able to reproduce. It's not reproducible anymore, so you don't get the crash at all. So this is an interesting bug to triage. Yeah, I think it's a good place to stop for questions. There are a few questions in the chat, I guess. So Viber asks, are CWise and Reduce the same tool? Yeah, I think yes, Reduce and no, in the sense that they based on similar philosophies. So CWise was developed after that. It's based on Python, and it's inspired by Reduce, and it uses the same Clang Delta tool that Reduce uses to do some of the source-to-source transformations. So what the orig format? So Farhan asks, what's the orig format? So do you mean by the multi-return.cpp .org? So he also asks, also, did you run the CPP file inside an SH and then run that on another SH? Yeah. I mean, it resulted in a segmentation fault, and when it's I don't know how to capture that segmentation fault in the script, because I have to grep for the in the output that's generated during compilation, I have to look for segmentation fault, but I was not able to capture that into a output file. So what I did is I wrapped that around in another script, and then able to dump that segmentation fault string into a file and then grep for that. So you can do all sort of these things. So that's why it's powerful that you can have these layers of um, you know scripting on top of the base script, and you can do anything with that, right? You can invoke a whole bunch of programs and just look for the interesting points that you're looking for in the output. So yeah, that's the powerful of the delta debugging design which Reduce inherited. So curious to know how the parallel operation really work within the tool. So that's um, that's an interesting thing. I think most part we are not going to look into it because it's each tool has its own strategy to do parallelism. I think I'll allude to what C-Reduce does. Um, but yeah, each tool has its own way of parallelizing it, and Google has this tool called half empty, which is developed as a parallel implementation of C-Reduce, and yeah, they have their own. Each tool has their own strategy to pick an interesting variant and then explore the reduce version. So it's basically a tree reduction, and you develop a heuristic to see which part of the tree or the branch is interesting to you, and then do the parallel version of that. I hope that answers the question. So can C-Reduce used to catch concurrency issues like atomicity violations or race conditions? Well, so C-Reduce is agnostics of uh, what you decide to get out of it, because it's just a reducer program that looks at code and just strips away pieces of it and then runs a code to runs a script that you give on it. So most of the things, like I said, like I said in the slide, where what is the interesting thing that what are the interestingness test should do is that it should look for programs that or it should be designed in a way that it looks for those cases like catching concurrency issues or atomic violations. So you should build that into the test or the script that we use to reduce. I don't think that C-Reduce is bothered by what you're interested in. It's just a script that strips away code and then and then does these reductions for you. Yeah, most of the thing you have to bake that into the script. Uh, Another question is that will this work for any language that Clang frontend has support for? Yes, of course. It uses the Clang frontend for doing some of the source-to-source transformations. But yeah, I think people have used that to for other languages like Rust, because the core itself is language agnostic. You can plug in different transformation passes. So some of the transformation passes are written in Perl that's language agnostic, and you can plug a Rust-based front-end based reducer or a transformation that runs on Rust code. So yeah, it's by most but the core of it is language agnostic, but the tool itself works on mostly C, C++, and OpenCL programs that Clang supports. I think people, yeah, like I said in the first slide, people have used for other languages as well. I'm a bit confused. Like when you say interestingness, how does the tool map it back to the line in the original program? Because the code is fully compiled and executed, does it run in an instrumented way with a secure environment? And basically, with each pass, it adds a flag which uses it to locate. So the flag part, no. So the tool itself looks at the source program. Okay, it doesn't care about the compiler flags you pass or anything. It just executes the script on the program, and when it does, it looks for, so at the first, the C program that you provide, the reducer runs that script, and it expects it expects the output to be 0 because at the first instance you want uh, the the C test case to produce a segmentation fault, a compiler bug that you're looking for. That's the first sanity, and then the tool starts removing pieces of code that doesn't care about any compiler flags. It's just plays with the source text of the program that you provide, and then again it passes those variants, the the reduced variants to the script that you give it. And then each depending on the output of the script. So if the script returns 0, then it's interesting, and if the script returns 1, then it's not. So those uninteresting variants are discarded away, and this tool recursively starts diving into those variants. Yeah, it's a big answer. Yeah, I hope that's useful. So Farhan says, so it starts removing and looks at the seg fault and whatever the program was, and thus reduces it. So I think if I read it correctly, so it starts removing and looks for the seg fault or whatever the problem that was. Yeah. So whenever it runs a script, it looks for the seg fault. So that's what I try to pipe it in the second script. So when it visits the seg fault, I grep for the out.log for segmentation fault, and that's what is the found as interesting. So if the program doesn't result in a seg fault, then it's not interesting. It's discarded away and does not require further reduction. Okay. Yeah. So got it. Reduces the code and recursively calls itself. Yeah, that's right. Yeah, so this is the bug that triggered the seg fault, and the user attached a preprocessed test case with 24,000 lines of code, and the reduced test case is now like 5 lines. That still produces the seg fault in the compiler. So can we use C-reduce to optimize programs? Uh, I think I try to answer this in the first place, but yeah, it's good to think about this from a general compiler point of view, because a lot of the C-reduce transformation passes include compiler optimization passes like simplifying expressions, copy propagation, dead variable eliminations. So whenever you remove all the references of the program, the definition of the program, so definition of the variable is not needed. um, and there are scalar replacements aggregates. So there are and you can also see it also runs function inlining pass. So it functions like a compiler for that matter, but hypothetically you can write a matrix multiplication program and tries it and give an output script that looks for different the results of the matrix multiplication, and you can ask the reducer to reduce that to a small program. I don't know if you can call it the optimized one, but hypothetically you can do it. But that is the difference between a reduced program and an optimized program. Yeah, so not really. And so, so that's an interesting question to think about, to see how uh, the internal subsidy reduce works. And so this is a high level overview of or pseudocode of how or reducer would work. So it takes an original test case, and it takes a size. So C-reduce also tries to get the size of the program as a parameter for reduction, and so and it goes through the pass list, and for each pass it it gets a list of each pass is a transformation. So it provides a variant to the transformation, and it runs a transformation pass, and then it checks the variant is interesting. So if interesting, would output 0 or 1, and based on that the variant is considered for next iteration of the transformation. And then in the else it does the advance of the current program. So the if the variant is interesting, then it's set to current, and then you advance that for the next iteration, and you do that until you cannot further reduce the program. So that's what a fixed point mean. So limitations, you can see that for a small test case, it took like a minute or minute and a half max, and for a larger test case, it took me more than an hour to run it. And test case reduction takes time, but it comes at an a long-term payoff where you don't have to run a larger test case again and again in your CI/CD pipeline. So if you have a unit test framework, you don't have to attach a large test case and then run it over on a per commit basis. So this typically happens when a test case early in the phase. So it's slow because in the early passes it's not able to reduce a lot of lines of code. So you have to uh, so if the first few passes, like the line pass, is not able to remove a lot of lines, then you'll start spending time in the subsequent passes on each of the um, each of those lines that are not invalidated, and you start doing all these transformations. That so the subsequent transformations take a lot of time, and yeah. So so there are cases where the highly templated C++ sometimes forces C-reduce to terminate with an unexpectedly large code. So debugging templates are very hard, and C-reduce is also the person that suffers from it. Yeah. A small minority of compiler bugs appear to be impossible to trigger using a small test case. So there are some cases where it's not able to reduce it reduce further because those are limited on the nature of the compiler itself. So for example, if there's a register spilling code that requires a test case to have enough registers to spill. So the program for you to trigger a bug in the register allocation, you'll need a large program that has a lot of registers, and that it triggers the bug. And the bug in the logic for emitting long offset jumps requires a test case to contain enough code that a long offset is required. So there are unavoidable test cases where large tests still required. So yeah, I think there are corner cases on that. So now going back to other programs that exist. So C-Reduce was the initial tool that was developed by the John Reggett team at University of Utah, and there are some other tools that spawn based on it. So CWise is a super parallel Python port of C-Reduce. The port is compatible to C-Reduce, so you can use it as a drop-in replacement for C-Reduce, and it uses the same efficient LLVM based C++ reduction tool Clang Delta. So we'll talk about how Clang is being used here in the next talk. But yeah, it uses the Clang front end as a source-to-source transformation for doing some of the the later passes in C-Reduce and CWise. So it's very easy to install. So I had very hard time trying to get C-Reduce to build properly and make it work, because it depends on Perl and a lot of other stuff. And I gave up on that and then installed CWise. It was very easy. You can just do the app install CWise. And there are other tools like Half Empty, which is from Google Project Zero, that which also reduces in parallel. So there are other tools. I think we saw CWise and LLVM Buckpoint. So LLVM Buckpoint is a similar tool that narrows down source of problems in LLVM tools and passes. So it can be used to debug three types of failures, like optimizer crashes, miscompilation by the optimizer, bad native code generation, including problems in static and JIT compilers. So LLVM is a versatile tool. It's not just a test case reduction. It can be used to debug failures in the LLVM compiler itself. And Buckpoint is a very complex tool. I cannot go into the details of it, but it's a complex tool, and it deserves a talk on its own. So it has a crash debugger, a code gen debugger, and a miscompilation debugger, and various components that goes beyond basic test case reduction. At one point, there was a redesign of Buckpoint to be more like C-Reduce. I think later there was another tool that's developed that's called LLVM-reduce, which works in a similar fashion to C-Reduce. So it's structurally similar to it. Has the same command line arguments. Um, or similar command line structure. So you can see that it takes a test script and the seed file, and it also so the difference here is that instead of running any C-based transformations, you run LLVM IR-based transformations on those tests. So each pass implements potentially reducing transformations at LLVM IR, such as removing instructions, metadata, functions in the LLVM IR. So LLVM reduce is more considered like a domain-based reducer. It considers LLVM IR structure instead of a general reducer like a delta debugging. There's also mlir-reduce. So mlir-reduce is a tool that's used to reduce mlir programs. So it's similar to bugpoint, a tool that can reduce the size of mlir input. It supports reducing input in several ways. So the interesting case about mlir is that you don't have you have operations, and each of these operations can be part of different dialects, and those dialects, the semantic of the dialect is important for a better reduction. Right. So this is again a domain-based reduction because you're focusing on just MLIR, and MLIR reduce allows you to register custom dialects for that. So it's a tool that's derived from, it's based on LLVM reduce and C reduce. It uses the same philosophy, but it has more domain-specific information or the structure of MLIR code. And you can, as you can see, it does a similar thing. It takes a test script and it takes an input, and they also have this reduction tree mode that allows you to discard variants more efficiently. So I think that's the end of the talk. That's so test case reduction is a very simple topic, and as you can see, it takes very little information to get started. And I've attached a lot of different blogs. Especially the first link is very interesting. Most of the slide itself is derived from the talk. It's very derived from the blog. It's very detailed, and I would recommend you guys to check it out. So, do you guys have any questions? I think that's the end of the presentation. Yeah. So, could you summarize CYs again? Kind of missed out use on the use slash main point of CYs. So CYs is almost the same way as C-reduce. It's a Python port. It uses the same mechanism that C-reduce uses. It uses the Clang Delta uh, tool or a plugin that C-reduce uses to reduce C or C++ or OpenCL programs. So in the working by CYs is similar to C-reduce. Yeah. But it's more of a Python slash a parallel version of C-reduce. Yeah, so Ashutosh also shares a link to the WhatsApp chat, WhatsApp group that we've created to discuss about the topics that we discuss in the series. So please join that link and ask questions. So here's a link to the slides which you can use for reference. So JP asks C reduce followed by manual reduce to isolate code. Okay, JP has shared a link where there was a partially reduced test case using C reduce. Yeah. So I think if you look at the LLVM's bug reporting page, so eh, I think I'll share that as well. So you can see that they point to a list of tools, and C-reduce or C-wise is one of those tools that can help you submit a bug with a reduced test case. So it's kind of recommended by folks in the community to use such tools and produce a reduced version, so you can be triaged and fixed much sooner. Again, yeah, I'll post a recording of the talk on YouTube. You can find that in our YouTube page. And I think, yeah, as usual, we'll go over the list of links that will help you to get up to date on compilers. For example, LLVM Weekly is a mailing list that's prepared by Alex Bradbury, and he sends up every week on the interesting things that happened in the compiler community, like blogs, commits from LLVM, Clang, and other projects. And it's the best place to get started or get up to date on LLVM. And there is a LLVM Discord server. It's more of a chat-friendly place where you can reach out to people in the community about anything that you want to know about LLVM, and they have different sub channels specific to projects, incubator projects. We also have an India specific channel. You can join and ask questions. We also post meetup updates there as well. There is a much more formal LLVM discourse page where it's more of a forum where you can post questions and you know get also community updates from there. It's also a good place to know what's happening. And of course, LLVM YouTube page where you can get a list of where most of the talks from the LLVM developers meeting, Euro LLVM developers meeting, and the CGO LLVM workshop, and all of that are posted. There is also the interesting initiative by LLVM Foundation about the LLVM office hours. So it's an interesting concept where there are folks, people who maintain portions of LLVM, like the mlir project, or the attributor framework. So folks who are expert in their field, they set off the slot like an hour in their calendar, and you can join a Gmeet chat, and you can ask them questions directly. So this is more of a friendly reach out, and you can join and talk to them and have your questions answered. So if you go to that office hours page, you'll have a list of people who have um, uh, who who are available, and you can look at the calendar and the list of topic they are interested to discuss. And join the Gmeet chat and please ask questions. And there are project specific meetings. So this is more of a technical meeting um, where they develop more of a developmental work, development in MLIR or RISC-V. So people who work on those projects, they sync up on a bi-weekly or a monthly basis. And of course, there is our LLVM YouTube page where you can find the recordings of the meetup. I think that's the slides that I had. So any questions?
Hi, Pradeep. I have a question. Vinayaka here.
Hey, hi, Vinayaka.
Yeah. So this question is not related to like exactly reduction of test cases, but is kind of related. So when there are non-deterministic failures in the compiler, right? They might be treated as passes. And is there any tool that kind of catches it? I'm just continuing the question that was asked by Arjun Acharya.
Okay.
Whenever there are races inside a compiler.
So your voice is getting lower. Can you speak up, please?
Oh, sorry. So my question was, is there any way we can detect compiler bugs where the bugs are basically because of they are non-deterministic bugs?
Okay.
As in, for them, reducing a test case is very hard, right? Because once you run it, it will pass, but next time it will fail. So my question is not directly related to the C-reduce, but I was just thinking in terms of can I reduce a test case for a non-deterministic bug?
Well, you can still run a C-reduce or a reduction, but you might not be you might not end up with a optimal reduced version, right? There are cases where if the test is interesting, but the script itself returns a non-negative number, which means that the test that's determined by the script is not interesting, right? The code itself is interesting, but the script returns otherwise. So the reduction will not go through, and you'll end up with a bigger test case. So yeah, you'll not end up with an optimal one, but yeah, at least you can try and give it a shot. Yeah.
Okay.
But I don't think there is a tool for a non-deterministic version of it. Yeah, I don't, as far as I know.
Okay.
I don't know if there's any, just chiming in here, I don't know if there's anything for all non-deterministic test cases, but there is a tool we have for OpenMP race conditions. So it's called Archer. I'll just put a link in the chat. So we use it for race conditions, and like race condition programs are the sort where if you run it like 100 times, once or twice, you hit the bug, and sometimes you don't.
Yes.
So Yeah, so
Yes.
there's an Archer tool. It's on GitHub. So maybe you can check that out. I've put the link.
Thank you.
Yeah.
That's it.
Yeah, thanks for sharing, Ashutosh. Yeah, I think this is also similar to Arvind's question. Yeah, whether we can catch concurrency issues like atomicity, race conditions there. Yeah. So another question is that a core dump can point exact point of the seg fault that happened. So these tools are used to use side by side. So I'm not sure if I understand it correctly. Not necessarily. So you want a reduced version of it. So here we are trying to reduce a test case that reproduces a seg fault, and so you don't want to run GDB on a very large one because it takes time to load, and it takes time to parse the program and run it. Load the program and run it, and then point to the line of code that results in a seg fault. Um, but yeah, as you said, yeah, they can be used side by side, but it's good to have a reduced version. So one, you compile it, it takes fewer steps to compile because you're compiling a small version, and obviously GDB requires a debug version, and when you compile it, debug, you get a lot more information like line like source line information and a lot of debug information that's attached to the original program. And it takes time to load larger programs. Yeah, I think like I said, these tools can be used side by side, but yeah, it's good to provide a reduced version of it. You mean dump of a reduced code? I don't think segmentation fault would give a dump of a reduced code. Does anybody know an answer to this? I don't think a segmentation fault can provide a dump of a reduced code. Or if you can provide me more details about it here or in the WhatsApp group, yeah, I can get back to you on that.